number of chemical reactions we conduct every day is remarkable. The ways we metabolize food, the ways we obtain and use energy require innumerable chemical reactions that often go unnoticed. Many of these reactions involve the transfer of electrons from one chemical species to another. This exchange of electrons is called oxidation and reduction, or redox. The oxidation of materials can cost untold sums to industry. In 2002, the annual estimated loss due to rust was $276 billion, or over 15 times NASA's annual budget. Because of this, we go to great lengths to create and use materials that resist damage due to oxidation.
Preventing damage to infrastructure isn't our only preoccupation with oxidation. Preventing oxidative damage to our tissues has generated a multi-billion-dollar vitamin or antioxidant industry. Not all oxidative processes cause damage. In fact, some can be quite useful.
We're addicted to the oxidation of hydrocarbon fuels, a process that has fed our growth from the Industrial Revolution to the space age. To extract energy from food, a critical example of a redox process occurs in our cells, where we harvest chemical energy through the oxidation of food. Dr. Seth Elsheimer is an endurance runner and organic chemist at the University of Central Florida.
Cellular respiration is a series of complex reactions wherein food molecules get oxidized ultimately to carbon dioxide and water. Those reactions are largely oxidation reduction, or redox reactions. There's a series of respiratory enzymes involved, and the coenzyme of those is nicotinamide adenine dinucleotide, or NAD. It gets reduced to NADH.
To understand both parts of the redox process, it's helpful to separate them into half reactions.
For example, sodium metal reacts with chlorine gas to form ordinary table salt. In this reaction, the sodium loses an electron. The sodium is the oxidized ion in this reaction. The chlorine gas gains an electron from sodium. This is the reduced portion of the reaction, since the charge of chlorine is reduced. Since the chlorine gas must gain 2 electrons to balance the reduction half reaction, the oxidation half must have lost 2 electrons. When both halves are combined, the net reaction shows the net redox process.
Separating the redox equation is helpful in understanding the processes, but is ultimately artificial. One species cannot be oxidized without the reduction of another. For that reason, we call the species that is being oxidized the reducing agent, and the species that is being reduced the oxidizing agent.
For example, when iron rusts, the uncharged elemental iron forms iron 3+ ions. The iron loses electrons to become positively charged, so the iron metal was oxidized and was the reducing agent. By contrast, the elemental oxygen is uncharged at the beginning of the reaction, but now has a -2 charge when the rust has formed. Since the charge was reduced, or became more negative, we know the oxygen gained electrons and was the oxidizing agent. The mnemonic oil rig can be helpful in remembering that oxidation is losing electrons, and reduction is gaining electrons. Here's a reaction for you to try. Can you identify which reactants were oxidized and reduced? Which reactant was the oxidizing agent? Which was the reducing agent?
Once we understand redox reactions, we can use them to our advantage. If you've ever bleached your hair, it's likely that you used hydrogen peroxide to oxidize melanin, the pigment that gives dark hair its color. Jewelry designers use redox reactions to electroplate oxidation-resistant materials, like rhodium, onto precious metals that are usually susceptible to tarnish, like silver.
Artists can use redox reactions to create artistic effects with oxidized metal patina. One example of this patina is the green oxidized copper on the Statue of Liberty. A film of green copper sulfates, copper carbonates, and copper chlorides coat the exterior of the once reddish luster of pure copper. Professor Ryan Bisons, an artist at the University of Central Florida, uses redox reactions in his artwork.
This is a piece that I made out of cast iron, and it has iron oxide on the outside, and I left this one out in the elements on purpose, getting rained on and everything. And the iron has some carbon on it from the molding process, but most of it has reduced its protective layer, and it become kind of reddish and oxidized. And on the back side, we have some oxidation as well. However, I've ground back into the metal to give it have a polished effect, and you can see the chambers in the shape a lot better. I mean, that's even my simplest studies are about integrating science into art. Every artist has a language that they speak, and that's the language I speak. I like to talk about different aspects that interest me, about the universe, or just simple geometry, or complex geometry, or I try to look at something that I find beautiful in nature and then emulate it in artifice in my work.
Although oxidation in nature can cause some serious damage, engineers have used redox reactions to create and store energy. The most common example of this is the battery, which uses redox reactions to store and distribute electricity. A voltaic cell is an electrochemical cell that derives electrical energy from spontaneous redox reactions taking place within the cell. It generally consists of two different metal electrodes, a current of electrons spontaneously flowing from one to another. Which is oxidized and which is reduced depends on their reduction potential. If more current is required, a more sophisticated voltaic cell can be constructed. To make a voltaic cell, metal electrodes, in this case iron and copper, are connected and placed in electrolyte solutions containing metal cations. A salt bridge is used to complete the circuit, allowing ions to flow from one side to the other, preventing the buildup of charge at the electrodes. In contrast to voltaic cells, for which oxidation and reduction occur spontaneously, we can deliberately oxidize or reduce a certain species with a battery or power supply to generate the current we need. This is shown with the electrolysis or decomposition of water into its elemental components, hydrogen and oxygen. To electrolyze water, a non-spontaneous reaction, we use an electrolytic cell, which requires a source of power. The battery supplies a current to reduce water at the cathode. Different gases are produced at each electrode. The hydrogen and oxygen are produced in a 2:1 ratio, which means that we can tell which electrode is the cathode because twice as much hydrogen gas is formed relative to the smaller amount of oxygen gas. Another way to tell is by the production of acidic hydronium cations produced at the cathode, which turns our indicator solution yellow. Electrolysis of water is one way to produce pure hydrogen, which is attracting more attention as an alternative fuel. We'll resume our busy schedule of performing oxidation reduction reactions while we drive, prepare food, eat, sleep, and breathe, but we'll have a little more awareness of the balance we strike between the give and the take in the redox processes occurring around us.